Welcome. My name is Sinan Özgün, and together with my colleague Annemarie Rickmann, we are presenting our work called Importance-Driven Continual Learning for Segmentation Across Domains. In this work, we explore the effect of importance-driven regularization methods in an incremental domain learning setting, where at each point in time a new magnetic resonance imaging scan is retrieved. The task is to segment out brain structures. This setting poses a challenge as neural networks can be sensitive to shifts in the input distribution that emerge from changes in the acquisition protocol, the use of different scanners, or age differences of the subject. Our goal is to create a network that is able to continuously learn and adapt to new domains while retaining prior knowledge. However, fine-tuning a neural network without the access to old data often results in a deterioration of the performance on prior datasets. Neural networks are especially prone to this phenomenon known as catastrophic forgetting. As seen in the figure, we trained a segmentation network with naive fine-tuning as well as using our proposed continual learning method. Whereas both approaches result in good performance on the fine-tuned domain, the continual learning model outperforms the naive approach in the performance on the older domain. To better define the continual learning setting, we selected a set of Desiderata that we applied throughout this work. The first point summarizes the core idea of continual learning, that is, methods should be able to adapt to new tasks while retaining knowledge about older tasks. In our setting, we didn't reuse old data samples, which is especially beneficial for medical applications where access to old data samples can be infeasible. Furthermore, a continual learning method should be able to work over a long period, and the model should not be aware of the task or domain a data sample belongs to. That is, the network should not have access to so-called task labels. In the literature, many different techniques for continual learning have been proposed that can be grouped into three main categories. Replay-based methods range from naive rehearsal methods that store a subset of old data to pseudo-rehearsal methods that approximate previous samples using generative models. Prior-based regularization approaches define a regularization loss that penalizes the shift of important parameters when the network is fine-tuned on a new task. Parameter isolation-based methods assign different parameters in a network to each task. This can be achieved by either fixing the architecture or dynamically extending the network. Most regularization-based and parameter isolation-based methods introduce an importance metric for each of the network's parameters. Our work is based upon this importance-driven approach, which we adapt for medical image segmentation. Particularly, we are building on top of memory-aware synapses, which is one of the best-performing prior-based continual learning methods. MAS computes importance weights for the network's parameters in an unsupervised fashion. Whereas this method employs the importance weights by introducing an additional surrogate loss that penalizes the change of important network parameters, we introduced two alternative approaches of regularizing the network. We refer to the first approach as MAS-LR. Here, we define a parameter-specific learning rate such that the learning rate becomes a function of a parameter's importance. Hence, the learning rate of important parameters will be reduced, while it will be kept the same for non-important parameters. While the surrogate loss in MAS indirectly penalizes changes of the parameters, learning rate regularization provides a more direct means to avoid changes to important parameters. But the soft penalty might not be sufficient to enforce the network to retain old knowledge. Taking inspiration from network pruning methods, we propose our second approach, which is called MAS-LR Beta. The idea is to freeze important parameters during the training of a new task and only fine-tune unimportant parameters. This approach can be interpreted as a hard regularization. Each domain is assigned a hyperparameter beta, which defines a threshold of how much of the network can be frozen in each step. Most prior-based approaches define importance weights for each parameter of a network. This can be quite cumbersome for larger networks as it doubles the amount of memory needed to save the model. In our experiments, we observed that the importance values within a convolutional kernel are similar, which is expected due to the shared functionality of parameters in a kernel. In addition, values within a filter also had similar values, even though the similarity within a kernel was higher. Hence, it would be meaningful to assign importance weights on the level of kernels or filters, instead of single parameters. The filter and kernel importance can be easily integrated into the proposed regularization of the learning rate by averaging all weights within a kernel or filter respectively.
In our experiments, we use the QuickNet architecture, which is a state-of-the-art network for brain segmentation. But our methods can be used with any deep neural network. We use MRI scans of 3 different data sets and segment them into 32 classes. For the task of continual domain learning, we split the data into 4 domains using the source of the data and the age of the patient. For example, our first domain contains scans of the CANDY dataset with an average age of 10 years, and the second domain includes patients of the ADNI dataset with average age of 88 years. We trained the networks using a combined cross-entropy and dice loss and use SGD with momentum as optimizer. We train for 12 epochs on each domain and start with a higher learning rate on domain 1 and reduce the learning rates for the succeeding domains. To evaluate continual learning methods, it is important to not only focus on the improvement of catastrophic forgetting, but to also consider the accuracy over time and knowledge transfer to unseen domains. We first define the train test accuracy matrix R, where the rows define which domain the model was trained on, and the columns define which domain the model was tested on. Each entry is the mean dice score over all classes. For example, entry R21 describes the dice score of a model trained initially on domain 1, fine-tuned on domain 2, and evaluated on domain 1. We adopt some of the metrics proposed by Diaz-Rodriguez et al. First of all, transfer learning is the average of the diagonal of R and measures the plasticity, meaning the ability to adapt to new domains. In our continual learning setting, we are mainly interested in the effect that learning a new domain has on the performance on older domains. The performance can either degrade in case of catastrophic forgetting or ideally increase. To evaluate this behavior, we measure the backward transfer, which can be split into 2 metrics. Remembering measures the stability of the network, meaning the ability of the network to retain its knowledge, so this metric assesses the effect of a continual learning method on catastrophic forgetting. Positive backward transfer measures the improvement of the network on old domains after learning a new domain and is generally very hard to achieve. The continual learning dice score combines the transfer learning and backward learning abilities of the network and is the most generic metric to evaluate continual learning. This metric is calculated as the average of the entries of the diagonal and below the diagonal of R. Finally, forward transfer is the average performance of the network on unseen domains, so that means the entries above the diagonal. This metric is an essential indicator of the network's ability to generalize well on unseen data. Here we show some results in terms of train test accuracy matrices for the lower bound baseline, which is just fine-tuning consecutively on the 2nd to 4th domain, and our MassLR continual learning approach. Our method improves over the baseline in plasticity, which is the gray diagonal, and stability, or backward transfer, which is the orange part below the diagonal. We can also observe that improvements in backward transfer are greater when the domains differ more. For example, the catastrophic forgetting on the first domain is highest after fine-tuning on the second domain, as these 2 domains differ a lot, and we can see great improvement here by using continual learning. In this table, we show the results of the baseline, naive fine-tuning, which can be considered a lower bound, and joint training of the network on a combined dataset, which is the upper bound for remembering and positive backward transfer. We can see that all continual learning methods outperform the fine-tuning baseline, and our proposed methods outperform standard math. As these continual learning methods are regularization-based, we also compare to classic regularization techniques like L2 and dropout, which we can see also improve continual learning ability. We then combined MassLR with dropout and can even observe a further improvement. Finally, we want to show some segmentation results on the first 2 domains for the fine-tuning baseline and our proposed MassLR method. Most striking here are the improvements in backward transfer on the first domain, as we can see in the zoomed-in parts. To summarize, we proposed a continual learning approach for brain segmentation across domains. Our approach, MassLR, uses importance weights that were introduced in math and defines parameter-specific learning rates based on these importances. It needs no additional hyperparameters and outperforms the standard math approach. It can further be combined with additional regularization, such as dropout, to boost performance. Thank you for your attention. If you have any questions, feel free to drop us an email and check out our code on GitHub.